Okay, so the substitution rule. I am not plugged in. Okay. All right, there we go. Okay, so the substitution rule. Substitution. So what's the substitution rule? Before I get there, let's remember what I said last time. Substitution rule is basically chain rule in reverse. Okay, so let's review the chain rule first. So what does the chain rule tell us? The chain rule. Chain rule says that if I am taking the derivative of f of g of x, so here I have the composition of the functions f and g. Cap f is the outside of the composition, right? G is the inside of the composition. Then what's the derivative? The derivative is given by, you take the derivative of the outside function, but you evaluate the derivative of the outside at the inside function. So once you take the derivative of the outside function, you replace x by g of x in the derivative formula for the outside, and then you multiply by the derivative of the inside. Right? That's what chain rule tells you. For example, if I am taking the derivative with respect to x of sine of x squared plus 1, right? Okay, so can someone tell me this function sine of x squared plus 1, that's the composition of what functions? What's the outside function here? The outside function is sine x, and the inside function is x squared plus 1, right? So by chain rule, what's the derivative? By chain rule, the derivative is the derivative of the outside, right? So outside being sine x, what's the derivative of that? The derivative of that is cosine x, right? The derivative of the outside function is cosine x, right? Derivative of sine x is cosine x. However, you have to evaluate the derivative of the outside at what? You have to evaluate the derivative of the outside at the inside, which means that you replace x by the inside, which means this, right? So take the derivative of the outside, evaluate it at the inside, and then you multiply by what? The derivative of the inside, which is what? 2x. Is everybody okay with that? Let's look at another example. Let's say I take the derivative with respect to x of, let's say, x cubed plus 1 to the power 7. Okay, so in this case, what are the outside and inside functions? What's the outside function here? Anyone? What's the outside function? X to the 7th is the outside, and x cubed plus 1, that's the inside. Notice that if you replace x by the inside, right? So if you look at the outside function x to the 7, you replace x by the inside, you get exactly the function that I have, right? Is everybody okay? So that is, if you put in this inside function for x here, you replace x by that, you get our function x cubed plus 1 to the 7. So now by chain rule, what's the derivative? By chain rule, the derivative is, you take the derivative of the outside function, which is what? 7x to the 6, right? That's the derivative of the outside. However, you have to evaluate the derivative of the outside at the inside, meaning that now you replace x by what? The inside of that composition. And then you multiply by the derivative of the inside, which is 3x squared. Is everybody okay with that? Is that okay? All right. Now let's recall the chain rule in a different format, right? So remember that if I have, let's say, three variables, y, x, and t, three variables. And let's say x and y are both functions of t. X and y are both functions of t. And let's say y is also a function of x. Is that clear? We are saying x and y both functions of t, y is a function of x, okay? So then, suppose, what is the derivative of y with respect to t? Well, I can, by chain rule says that I can write the derivative of y with respect to time as the derivative of y with respect to x multiplied by the derivative of x with respect to t. Am I making sense? Is everybody, since y is a function of x and x is a function of t, I can view y as the composition of x and t. Am I making sense? Y is a function of x is a function of t, so I can think of y as a function of t via the composition of the function y as x. So I can think of y as y of x of t, right? Am I making sense? X is a function of t, and then y is a function of x. So I can think of y as the composition of two functions. Is that making sense? So then the chain rule says dy dt is dy dx times dx dt, okay? You agree with that? Am I making sense here? So here is the composition. So what's the derivative of the outside of the composition? Dy dx, and then you take dx dt. Okay. So that's another form of chain rule here. And now let me come to the differentials. So how did we define differentials? Well, last week we said, well, if I take y to be f of x, then the differential of y is f prime of x times differential of x, right? So if y is f of x, then we are calling dy, with differential of y is f prime of x times the differential of x. Now, one problem here is that how do we interpret dx and dy? And like I said, a complete discussion cannot be done here, but the way you want to view dy and dx is the following. So how do you interpret the differentials? Notice that if you divide the equation here, so if you divide this equation by dx, then you get what? Dy over dx equals to f prime of x. So one way to view dy dx is that dx represents an infinitesimally small change in x, and dy represents the corresponding change in y. Okay? So when you take the remember, what is the derivative f prime? That's the rate of change of y. F prime of x is the rate of change of y with respect to change in x, right? Rate of change of y with respect to change in x. So you can think of dy as a change in y, dx as a change in x. Okay, so when you take the ratio, you get the rate of change of y with respect to change in x. So that's one way to interpret these differentials. Another way of interpreting it is that you can think of dy and dx as rates. So think about having a third variable t, and you can think of dy giving you the rate of y with respect to t. And then the right hand side is giving you f prime of x is dy dx, right? Multiplied by dx would mean the rate of x with respect to time, t. Am I making sense? So think of the differentials as rates. So dy is the rate of y, dx is the rate of x, with respect to a third variable, let's say. Okay, dy, the rate of y with respect to t, dx is the rate of x with respect to t. So then if y is f of x, then I can say that the rate of y and the rate of x with respect to t are related by that equation. Am I making sense? Is everybody okay with that interpretation? So think of them as rates, and if x and y are related by f of x, then the rate of y and the rate of x, they are related by that equation. dy is f prime of x times dx. Okay, now don't think too much about this interpretation, okay? At this point, okay? Where are we going to use the differentials? In the substitution rule, you will see that the idea of differentials. So I'm going to think of this differentials as just a notational tool. Okay, this is a notation that's going to facilitate the computation of integrals by using the substitution rule. Am I making sense? It's going to help us in using the substitution rule. It's going to facilitate the use of chain rule in reverse. Am I making sense? It's going to facilitate the use of chain rule in reverse. Again, using the chain rule in reverse is harder than using it directly to find the derivative. So let's look at an example here first. Suppose that I have the integral which is 2x. Let's say I am taking the derivative with respect to x of 2x times 1 plus x squared cubed. And what is that derivative? Oh, you know what? I'm sorry. I don't want to take the derivative of that. I want to take the derivative of 1 plus x squared to the 3, right? What's the derivative? Actually, let's make it 5. Let's make it 5. What's the derivative of 1 plus x squared to the 5? By using the chain rule, it is what? 5 times 1 plus x squared to the 4 multiplied by what? 2x. Which is equal to what? 10x times 1 plus x squared. So if I ask you, hey, what's the integral of 10x times 1 plus x squared? Yes, thank you. What's the integral of this? What did you say? What did you say? The integral of 10x times 1 plus x squared to the 4 would be? What? Go ahead. It would be what? This is the derivative of what? The integrand is the derivative of 1 plus x squared to the 5, right? The integrand is the derivative of that. So that's the integral. Right? So what am I doing here? Well, I applied the chain rule. I got the derivative of that function, and now I'm using the chain rule in reverse. If I am taking the derivative integral of that derivative, I should be getting the function 1 plus x squared to the 5. Let's look at another example. If I am taking, let's say, if I am taking the not the integral, if I am taking the integral, if I am taking the derivative, of sine of x squared plus 1, then I would end up with what? 2x cosine of x squared plus 1, right? Isn't that what we got when we applied the chain rule? We got sine of x, cosine of x squared plus 1 times 2x. Now if I ask you, hey, what's the integral of 2x times cosine of x squared plus 1 dx? What did you say? That would be sine of x squared plus 1. Again, if I apply the chain rule, I get that the derivative of sine of x squared plus 1 is 2x times cosine of x squared plus 1. Now if I use the chain rule in reverse, then the integral of 2x cosine of x squared plus 1 should be sine of x squared plus 1, right? But let me ask you this. Suppose that I didn't show you the derivative of sine of x squared plus 1, right? Suppose that I didn't show you the derivative of sine of x squared plus 1. We didn't do that step. And suppose that I gave you this integral here. I gave you the integral of 2x cosine of x squared plus 1. Would you be able to give me this answer, sine of x squared plus 1 plus c, right away? No, right? If I didn't give you this part, right? If I didn't tell you the derivative by using the chain rule, coming up with the integral of 2x cosine of x squared plus 1, right? Somehow doing the chain rule in reverse in your head and coming up with that answer is not something that you usually could do, right? Am I making sense? So we need to be able to use the chain rule in reverse, but we need a mechanism to do that efficiently, okay? And that's where differentials come in. So let's see now how differentials play a role in computing, in using the chain rule in reverse. So let's say I take the let me take the derivative with respect to x of capital F of g of x. If I apply the chain rule, right? If I apply the chain rule, what did you say the answer is? If I apply the chain rule, the derivative of f of g of x is what? Yeah, f prime of g of x times g prime of x. Let's say we are going to denote capital F prime by lowercase f. So lowercase f is the derivative of cap f, meaning that cap f is the antiderivative of lowercase f. Then I could rewrite this as what? As f of g of x times g prime of x. You agree with that? Everybody agrees with that? So what do I have now? I am going from I'm going left. I'm going from right to left by applying the chain rule. If I apply the chain rule to capital F of g of x, okay, and I'm writing the answers on the left, so I'm going from right to left, applying the chain rule. What I obtain is f of g of x times g prime of x, right? But what do I want to do? I want to use the chain rule in reverse, right? So meaning that I am going to start with an I am going to start with the integral of this guy, f of g of x times g prime of x. And if I start with that integral, that means that I'm going to take the integral of this guy, which means that I'm going to take the integral of this guy, right? Can someone tell me what is the integral? What is the integral of the derivative of cap f of g of x? Yeah, very good. So basically the answer basically is, if I ask you to take the integral of the derivative of x squared, right? If I ask you find the integral of the derivative of x squared, right? Find the integral of the derivative of x squared, which means I'm asking you to find the antiderivative of the derivative of x squared, right? Antiderivative of the derivative of x squared. Well, that's x squared, right? The integrand is the derivative of x squared. So I'm asking you, find a function whose derivative is the derivative of x squared, right? Isn't that what I'm asking you? Find a function whose derivative is the derivative of x squared, right? That's exactly x squared. So my point is, this guy is x squared, right? Same way, if I am taking the integral of the derivative of f of g of x, so the integrand is the derivative of f of g of x. The integrand is not f of g of x, it's the derivative of f of g of x. So the antiderivative would be exactly f of g of x. Right? The integrand is the derivative of f of g of x, right? The integrand is the derivative of f of g of x. So what's the antiderivative? It's f of g of x. Okay, now I'm going to do a notational trick here. Instead of writing g of x, I'm going to replace g of x by u. But I'm going to keep in mind that u is g of x, right? U is g of x. So basically, what is f of g of x? F of g of x is the same as f of u when you replace u by g of x, right? Is that right? F of g of x means the same as having f of u, evaluating f of u at g of x, right? Evaluate f of u at g of x, that's f of g of x. However, what is f of u? F of u is the antiderivative of lowercase f, right? So this is the antiderivative of lowercase f. And of course I have u equals to g of x. So notice something great happened here, okay? You started with this integral here, and then you have reduced it to the integral of f of u du. Why is that nice? Well, because your integrand is much simpler. Am I making sense? Hopefully it's much simpler. Okay. So let's recap what we did. What we did was we started with the integral of lowercase f of g of x times g prime of x dx, and we ended up with the integral of f of u du, and of course u has to be evaluated at g of x after you have found the antiderivative of lowercase f. So what did we do here? So remember, this is what we obtained by using the chain rule in reverse, right? By using the chain rule in reverse, this is what I obtained. Now, notice what is the effect of using the chain rule in reverse. The effect is nothing but differentials, right? Notice that to go from left-hand side to the right-hand side, this is what you did. You took g of x to be u, and you took g prime of x dx to be du, right? So all I did is I took u to be g of x, and I take du to be g prime of x dx, right? If I make those substitutions on the left hand side, I exactly get the right hand side. Am I making sense? But this is exactly how we define differentials, right? If u is g of x, differential of u is g prime of x dx. So what's the point? The point is using the chain rule in reverse comes down to applying differentials. Okay? Now, another thing that you want to realize is that when is this going to work? Well, look at your integrand on the left hand side. The integrand has two factors, right? The integrand on the left hand side has two factors. What are they? One of them is the composition of two functions, right? One of them is the composition of two functions. The other one is what? What's the other factor in the integrand? There are two factors. One of them, composition of two functions. The other one is what? What's the other factor? It's the derivative of the inside, right? You have the composition of two functions f and g, and the other factor is the derivative of the inside, right? When the integrand looks like that, you can apply the substitution rule. Okay? And what are you taking u to be? You're taking u to be the inside of the composition, right? You're taking u to be the inside of the composition. Is everybody clear? Okay. Having said that, you need to recognize the integrand as the composition of two functions multiplied by the derivative of the inside, but usually you don't have to really think all that much about inside, outside, and so on. Let your gut feeling pick u. So what I said is pick u to be the inside, but I will also say that don't think too much about the compositions and whatnot. Just think about your gut feeling about what should be u. And you'll see as we do examples, as you have more and more experience in computing these integrals, you'll see what I mean. So let's look at some examples. Let me go back to my example of 2x times cosine of x squared plus 1. So I have to find the antiderivative of this function. Notice that, is this the product of two factors? Is the integrand product of two factors? Yes, I have 2x here, and then I have this guy, so it's a product of two factors. Is one of them the composition of two functions? And it's the composition of what? Cosine x and x squared plus 1 is the inside. And what's the derivative of that? Which is a factor in the integrand, right? So what should I pick for u? I should pick for u to be the inside of that composition, x squared plus 1. And then what is the differential of u? 2x dx. Right? So this is how I should be picking u. However, remember I said don't worry too much about the inside and outside. What is your gut feeling when you look at that integrand? You are trying to simplify the integrand. You look at that integrand and you say, hey, which one is the uglier part? Or you can say, what do I wish? Well, I wish that x squared plus 1 was just x, right? I wish x squared plus 1 was just x because that's my friend cosine x, right? So I would pick u to be x squared plus 1 and see what happens, and du would be 2x dx, and try to make substitution now. Well, this is the same as cosine of x squared plus 1 times 2x dx. I haven't done anything, I just rearranged the factors. Now I'm going to make the substitution. What is x squared plus 1? Well, that's u. And then what is 2x dx? du. So all I have is cosine of u. And then I know that the integral of cosine u is sine of u. And then at the end, what do I have to do? I have to replace u with x squared plus 1. This is exactly what we had before, right? So that's the antiderivative of 2x times cosine of x squared plus 1. Is everybody okay with that? I want to do the same problem again, but without the 2. So if I didn't have that 2, how does it change the problem? Well, let's see. Let me wait for everybody to finish. So my question now is, what if I don't have that 2? Okay, so let's erase. It's not letting me erase. So this is cosine of u. Let's say I have only x. How does it change the problem? Would I still pick x squared plus 1? Sure. I should still pick x squared plus 1 to be u. And then the differential of u would be 2x dx. And notice that then I could say that half of du is x dx. So remember that I don't have that now. I have x dx only, right? And now x dx becomes what? X dx is what? When I make the substitutions, I get x dx is what? Half du, not just du. And what should I do with the half? Bring it outside of the integral, because I am allowed to bring out any constant factor. So that's going to be, let me erase these 2 lines. That's going to be half of the integral of cosine of u du. And then I could say this is half of sine of u plus c. And that's going to be half sine of x squared plus 1 plus a c. Is everybody okay with that? Okay, what's next? I have explained how the substitution rule comes from using the chain rule in reverse. And using the chain rule in reverse comes down to using differentials. Okay? And that's why I said think of the differentials as a notational tool which will facilitate the use of substitution rule. Okay? What should we do next? Well, I am going to keep on doing examples after examples until you say that you had enough with substitution rule. And you ask me to stop on substitution rule. And then we're going to move on to something else. So we're going to do a lot of examples now on using the substitution rule with different types of integrands. So my next example is the following. Let's say I have the integral of x times the root of 1 plus, actually the cubic root of 1 plus x squared dx. What's this integral? Again, how do you choose, how do you pick u? Well, look at the integrand. Do I have 2 factors? Is one of them a composition? And what's the derivative of the inside of the composition? What's the derivative of the inside of that composition? What's that? What's that? 2x. Now 2 is not a factor in my integrand, but x is. And even if 2 is not a factor in my integrand, that's fine, because 2 is just a constant and we can take care of that. So my u should be 1 plus x squared. So that's one way of picking u, but you'll see that in many problems it's sort of hard to pick what is inside and what is outside. So let your hand do the job. That is, use your gut feeling about how to pick u, which means that look at the cube root of 1 plus x squared, and what is 1 plus, what would you wish? Well, you would wish that 1 plus x squared was just x, right? Because if 1 plus x squared were just x, then the integrand becomes a power of x, right? Am I making sense? If 1 plus x squared were just x, then the integrand becomes just a power of x. So you would wish that 1 plus x squared is just x, right? So let that be your guiding line to pick u. Okay, so u would be 1 plus x squared. And then what is du? That's 2x dx. Okay, and then I could say that half du is x dx. And then I could write this integral as what? I'm going to rewrite this as 1 plus x squared cube root of that times x dx. Okay, and now I'm going to make the substitution, and this would be cube root of what? U, and x dx would be half du, and this would be half. And what is the meaning of cube root of u? Cube root of u is u to the what? 1/3. So I took out the half outside the integral, and then we apply the power rule, right? So this would be 1 over 1/3 plus 1, u to the 1/3 plus 1. That's by the power rule. And this is half 1 over what? 4/3, right? U to the 4/3 plus c. And this would be half times 3/4 u to the 4/3 plus c. And then this is what? This is 3/8 u to the 4/3 plus c. And finally, I have to go back to my x, right? Finally, I have to go back to my x. So go back to my x would be, what was u? One plus x squared to the 4/3 plus c. Okay, that's the final answer. Now that I think for a second, I have to edit the recording. Okay, I made a big mistake here. My mistake is that I said I have to go back to my ex, right? So imagine my wife listens to it, right? That'll be terrible. So I have to change that. Okay.
Does your wife actually watch your recording?
Probably not. Probably not. Okay. So let me. Is everybody okay with this? Is everybody okay with this? Any questions? Everybody is okay? All these steps are okay with you? Okay, we are going to do more examples on Wednesday, okay? You have the homework that is due on Wednesday. It is involving questions like this. So make sure you understand this substitution rule.